Hello, everyone. First of all, thanks to Francis Xavier and Gregor for inviting me to give this seminar to this very interesting consortium. My name is Mahdi AZARPEYVAND, and as Francis Xavier mentioned, I'm a professor of aerodynamics and aeroacoustics at the University of Bristol. The topic that we've chosen for today is on the application of porous materials for aerodynamic and aeroacoustic purposes. I'm pretty sure you all know what aerodynamic is about, but I will spend a bit of time and talk about what aeroacoustics entails. The building you see there is called the Wills Memorial Building, which is right at the center of Bristol. It's part of the University of Bristol and is our flagship. So if at any point you visited Bristol, it's very easy to find that will be the door to the University of Bristol. We don't live in there. We live in an engineering building behind in a dark corner of that nice building. And there is a good reason why I have removed the sky from that picture. Okay, let's move. Right, so before I begin, I just wanted to give you an idea of where we are and what Bristol is about. So Bristol, as you can see, is this city, which is a medium-sized city, is about 700,000 people living there, and is in southwest of England. When the weather is nice, it's quite a nice city, and you can see I've only picked the pictures with blue sky. We have like 6-7 days a year like that. But when weather is nice, then we have a hot balloon festival near our suspension bridge, which is over 160 years old and is still functional. And you can see very nice architecture and very nice city. So at any point, if you wanted to visit, give us a shout and we will be happy to give you a tour of the city and the facilities. So Bristol, in terms of aviation, has a very long history. It goes well above 100 years. I'll put together some pictures for you here just to understand what Bristol had done to the aviation sector. Before World War I, several aircraft were designed and sold from Bristol. During World War I and World War II, that was when Bristol was quite active in aerospace, making the vehicles, the air vehicles for the war, obviously. And then the most famous perhaps is the Concorde. The first Concorde took off from Bristol to Poitiers, and the very last one in 2003 flew back to Bristol and went right into the museum. Again, we have a very nice aviation museum here, so if you ever come to Bristol, I suggest going to that museum as well and see the Concorde there. Why Bristol is important in terms of aviation industry, you can see it in this map. So that's the city of Bristol. We have the Filton, which is the old BAC, the British Aerospace Consortium, now home to almost all the aviation industries. We have BAE System, Airbus, Rolls-Royce, GKN, Fraser-Nash, which is a consultancy, Leonardo a bit further to south, GE Doughty and Safran further north. So you can see politically, we are very well placed to work with aviation industry, and that's what exactly University of Bristol does. Right, so let's move on to why aeroacoustic is important. Aeroacoustics basically mean whatever noise that is generated by an aerodynamic component. The aerodynamic component can be the wing, can be the jet engine, can be the rudder, can be the landing gear system, or a supersonic jet, the air coming out of a supersonic jet. Automotive, whatever noise generated from automotive, especially in the luxury sector, the side mirror, the noise from the flow over the tires. You can also think of the wind turbines. Noise from wind turbines is very important. If you install it and exceeds whatever the standard says, it can't operate. It has to be shut down and taken down. For the air conditioning units inside cars, especially now that we are moving to electric cars, this is becoming very important. You don't have the motor noise, so the dominant noise will be the air conditioning. And the human brain is a very funny thing. So when your body temperature goes up or goes down, you want the air conditioning to work, but as soon as your body settles, it starts picking the noise, doesn't like the noise. So a lot of research been directed to air conditioning noise, the fan noise. You can also think of the musical instruments, how the sound is created, how generated from instruments. So in a nutshell, aeroacoustic is important for aircraft noise, for automotive noise, for wind turbine noise, heating, air conditioning, wind instruments. And pretty much in the first three categories, we do have a standard. So we do need to meet these standards. If we don't, there will be consequences. For aircraft noise, they can't fly or they have to pay fine. For automotive, there is a competition, especially in the, as I mentioned, the luxury sector, there is a competition. The comfort is very important. Wind turbine, as I mentioned, if they do not, the onshore ones, if they do not meet the noise regulations, they can't operate. And this is a very expensive process to design, build, erect something, and then realize the noise is not what you wanted, then you have to take it down. Very costly thing to do. So let's focus a bit more on aircraft noise. There are several noise components. Jet mixing, the high-speed air plume that comes out of the jet engine that creates noise. Fan and turbine and combustor inside, they have a different noise signature. Airframe itself, it can be the wing or it can be the landing gear system. That also has a distinct signature. Fan and compressor from the inlet side. And you have the airframe noise, high lift devices, etc. There is a picture here. You see a typical 1960s design of a jet engine and a more modern. This is one of the Rolls-Royce Trent ones, probably 900. You can see how the technology has improved. Back in the 60s, the jet was the dominant noise source at the back of the jet engine. Now the jet has gone down massively, and other components like compressor and fans are more important. What does that mean is that the plume itself is not generating that much of noise, but the component inside the jet engine is making noise. And this is where all the cascade, all the blades, everything is and then we need to try to reduce the noise at component levels. You see how complex this the jet engine is. You have the fan, the OGV, all the cascade, and all these things, they will generate their own noise. Jet installation with the fan, with the jet engines becoming larger and larger, there is more interaction between the flow and the airframe system. This is something we call jet installation effects. And again, this has changed the noise signature of aircraft over the past few decades. Landing gear system itself makes a lot of noise, especially during landing. And a lot of effort has been put into reducing the noise from landing gear system. This is a high lift device, the wing and a slat. And again, you see that the noise is generated from the slat area and radiated. Why I'm presenting all these things? Because these are the noise signature, the noise generation mechanism is different for each component, and we need to come up with noise mitigation method bespoke to that particular component. You can see here a perforated sheet or a porous material that has been applied to the landing gear system. The same thing we have tried on the slat. We have replaced part of the slat with porous material, or put porous inside the cove to reduce the noise. So I will come to those in a bit. This shows the noise levels over the past 5-6 decades from different generations of aircraft. You have the turbojets up there. Obviously, there is no number, but you can see the delta. Turbojets, then first generation back in the 60s, and then second generation in the 80s, 90s. The current design between 2005 2015, and this is what the standard tells us where we should be by 2020. Well, now we are 2021, and I can tell you that we did not meet the standard. So there is pressure on industry to think out of the box and come up with new technologies. This figure shows it a bit more clearly. This is zoomed in version of that one. So you have a B 777 here, A340, A380. This arrow shows where we should have been by 2020, and we are here. We have missed that by a few dB in EPNL. And that again tells us that the traditional aircraft and traditional propulsion is not going to quite help us in terms of achieving noise regulation. So we need novel architecture, novel noise mitigation technologies to achieve the future standards. So what we do at Bristol, we cover a range of aeroacoustic applications. Some examples you can see here: airfall noise, cavities, jet engines, landing gear systems, and we try to get inspiration from from nature. So we try also to bio-inspired technologies as well. About 60–70% of our activities are experimental, are done in our aeroacoustic facility. You see a picture of that. I will come to that a bit later as well. But basically, we are covering almost all different components that I mentioned previously. An aeroacoustic facility, the one you see here, is basically a wind tunnel, but a very quiet wind tunnel that enables you to put something inside the flow and measure the noise signature from that component. You see some more clear pictures here. So again, the same thing here. This is the top view. There is a big fan down there in a separate room, and then the air is pushed into this long duct going all around the anechoic chamber, and then taken inside the anechoic chamber, and then it goes into the air goes into the room and collected by a huge collector, taken back to the fan. You may say that the wind tunnel is not a standard one, and I agree, it's quite a standard. The reason for that is that we do need a lot of space between the fan and the work in the test section to reduce the noise from the fan. So every single duct you see here is fitted with a silencer, quite a big one, to make sure that the fan noise is suppressed to the level that is good enough to put a stuff inside the flow here and measure the noise directly using this microphone array over the section. And this is the collector that I mentioned, is designed again for this nozzle to make sure that the room does not generate any recirculation, and also most of the air is taken back to the fan with minimum noise. The baffles you see here are part of the silencers, again, to reduce the noise from the flow interaction and also from the fan upstream of the flow. This is a picture of our group. I think the pictures are not the most up-to-date. There are a few people who have left, a few people who have joined, but it gives you an idea of the size of the group. Our group is over 20 people large. 60–70% of our research is experimental, but we also do some CFD and some analytical models. We are mainly sponsored by the Horizon 2020 and Clean Sky, and also EPSRC, which is the UK government funding scheme. We also have industrial collaborations with Airbus, with Doughty, Embraer, Vestas, etc., and a few other GKN, a few other companies. So let's move on to one single component from all the components I mentioned previously: airfall noise. Airflows are everywhere when it comes to producing thrust, torque. There are so many blades inside a jet engine, from the fan, from the OGV, from the cascade system. These are all categorized as blades and airflows. You have the wing, you have the blade of a wind turbine, the blades of a centrifugal or axial fan. These are all different families of airflows. And when it comes to the noise generation from them, they're generally categorized into 5 main categories. I don't want to take you through all the lecture notes from aeroacoustics, but just want to give you some general ideas so later we can go to results and better understand the results. So depending on the operation mode of an airflow, the noise can be categorized as either separation noise at relatively low angles. At higher angles, we have a stall noise. If you have a tip, you may have a tip noise. If your blade is flat back or is blunt, you may have some vortex shedding and associated noise. You may, if you're operating at very, very low Reynolds numbers, which is often the case, for example, in the case of small UAVs, you have laminar instability or TS wave noise. So these are the main categories of airflow self-noise, i.e. the noise that is generated because of the interaction of the airflow with its own flow, with its own boundary layer. I don't want to bore you with maths, but this equation is called the Amiot model for far-field noise. So you have the PSD, the power spectral density of the far-field noise, which is given by some factors. We don't need to worry about that. But these two quantities are the important things, and I will keep repeating these two quantities throughout my presentation. The first one is called the airflow response. So this basically means what is the airflow like? What is the geometrical properties of the airflow, the boundary conditions on the airflow? Do you have an elastic trailing edge or poroelastic leading edge, or is it a completely solid case? Are you considering it to be finite or semi-finite or what? So this is called the airflow stress noise. We don't need to go into the details. The second parameter is gives us the flow properties. So what type of flow do you have over the surface of the airflow? The technical term for that is wave number frequency, a spectrum of the boundary layer, but again, is basically, in a nutshell, is what the flow is like. So that's how the far-field noise theoretically is calculated. What also tells you is that if you want to reduce the noise, these are the two main parameters that you have to manipulate, you have to fiddle with. You either change the response function of your airflow. Let's say you change the trailing edge to an elastic trailing edge or a poroelastic trailing edge, or you manipulate the flow itself using flow suction, I don't know, some sort of rough surface or whatever that gives you that benefit to reduce the noise. If you're interested in knowing more about this thing, I'll put the reference down here from Roger Moreau from ECL Lyon. So to summarize that, in terms of noise control methods, we can generally put them into two families, passive methods and active methods. The passive methods, there are all sorts of passive methods tried over the past few decades on airflows. Serration is one of them. I have a few slides on that. Serrations can reduce the noise, either on leading edge or trailing edge, depending on the flow condition. Porous material, which is the main topic of my presentation today, I spend the rest of the hour on that. Surface treatments, this is something that we have also been working on. Again, is one of those bio-inspired ideas, shark skin in particular. So we have taken some ideas there, and we have demonstrated noise reduction can be achieved. Morphing technologies, active or semi-passive, semi-active also is something that we are considering. On the active flow side, flow suction, flow blowing, microjet, sweeping jet, you see a picture of that. All these things, plasma, all these things have been tried for reducing the noise. Again, going back to this equation, you can see that some of these things, for example, this one is changing the response function of the airflow. This one is changing the boundary condition and may also change the flow condition. So it is sort of fiddling with both parameters. If you use active flow, the airflow response is pretty much the same. What you're changing is the flow properties and reducing the noise by changing the flow properties. When it comes to overall performance of the system, passive active, we have to make a balance. We have to strike a balance. Most of the time, when with passive methods, they're easy to be implemented and they do not require energy intake. But with active methods, you need to put in that energy intake. And for aerodynamic purposes, that energy input can be very large. For aeroacoustic purposes, it can be lower, it can be smaller than the aerodynamic purposes, but still you need to think of that energy input that you need to put in. This slide summarizes the pros and cons of passive and active methods. Passive methods are usually very low cost, easy to be implemented, easy to install. requires no power input, but they are effective only over a range because they do not change. So if you have designed it for, let's say, low angles of attack or low Reynolds number, they may or may not work at a high Reynolds number or high angle of attack. And for the majority of cases that we have considered, they will also come with some sort of aerodynamic penalty, most of the time increased drag. On the other hand, active methods are effective over a wider range of operating conditions because you have the control system. For a majority of cases, you can both improve noise and aerodynamic, but they are more expensive to be implemented. They have maintenance issues, some more sophisticated layout, and worse than all is the power input. But as I mentioned, what we have demonstrated so far is that the power input for aeroacoustic purposes is lower than aerodynamic purposes. We need a lower energy, and we don't need to blow that much air or suck that much air to reduce far-field noise. I've put a picture of one of the things that we have been working on with trailing edge serration. You don't see the whole airfall, but that's the trailing edge, and you see what we call slotted serration. This was a patent that we did back in 2008 with Rolls-Royce. And as you can see, we demonstrated that we can reduce the noise over a wide range of frequencies using trailing edge serrations. The black solid one is the baseline, i.e. no serration. And when you add the serration, you reduce the noise by a good 3-5 dB over a wide range of frequencies from almost 500 all the way to 7,000, which is quite a wide range, and the implication is massive. Again, going back to the equation I presented before, by adding the serration, we are changing the response function of the airflow, and the mechanism that leads to the noise reduction, is destructive interference between the sound field that are generated from different edges. That technology has now been implemented in all sorts of applications. Over the past 10 years, almost every single wind energy company has adopted the technology. They have add-on components, add-on trailing edges, trailing edge serrations to the blades. New generation of blades, they have the serration with the blade. They don't need to add it to the blade. On the UAV, in the UAV sector, you can see people are doing all sorts of serration ideas, axial fans as well. They are trying, and they have demonstrated that they can reduce the noise by 5 dB. These are all now commercial. There is something to be worried about though. Academics tend to sometimes push it a bit too far, and I've seen all sorts of ideas and proposals out there to put serrations on everything. This one is a joke. I took this picture in TU Delft. They had a nice board, and they had put all sorts of crazy ideas that one may consider in the future, and this was one of them. So it's not serious, but it's just a joke. So let's move on to porous media, the main topic of my presentation today, and I try to cover both aerodynamic and aeroacoustic purposes. A bit of warning, this is I haven't put that much of equations in there, so it might be a bit boring for you, especially if you're coming from continuum and photoelastic area. I'm going to mainly present experimental results and try to show you some other application of porous media that you may not have considered before. So why is important? Because industry is considering porous media, porous materials for various applications. There are boundary layer control, wake and vortex shedding control, steady and unsteady aerodynamic forces, mitigating loading, controlling turbulence level in the boundary layer, in the wake, and wake interaction effects. I've put some pictures here just as an example of each category. So the one down here is for boundary layer control. We try to control the boundary layer by letting the boundary layer sinking inside porous medium. Bluff bodies, this is, you can think of landing gear system, for example. There are also the research being directed in that direction for reducing the wake and vortex shedding from bluff bodies. blunt trailing edges, which is as an example of a flat back airfoils, which is used in a wind turbine, and also turbulence interaction. Inside the engine, we have a lot of blades interacting with each other, so the turbulence from upstream components will interact with downstream components. Cavity, we had industrial project with Embraer that tries to reduce the noise inside the landing gear bay, or in case of military aircraft, bomb bay. So when the bay opens, you have a lot of instability, and we try by applying leading edge and trailing edge porous material, try to stabilize the flow inside that bay. A bit of literature review for you. The literature is quite rich in this area when it comes to the use of porous material for aerodynamic, aeroacoustic purposes. I've just put a few pictures to give you an idea of what is happening. This is a very old patent done in the US for marine type propellers. They applied porous material on a marine propeller, and they demonstrated that they can reduce the underwater noise. This is a CFD case that a South Korean group did, and they applied a trailing edge porous section, and they demonstrate that they can reduce the noise by applying trailing edge porous material. A similar work was done later in Germany by Aachen group, and they also observed the same thing. On the experimental side, another group in Cottbus in Germany have been working on porous trailing edge, full porous, and then partial porous. And again, from experimental observation, they also showed that noise reduction can be achieved if you use the right porous material for your airfoil. This is something that we did back in 2007-8 at ISCR in collaboration with DLR as part of the Flowcon project, and we also saw noise reduction from an airfoil with a porous section just upstream of the trailing edge. So the aerodynamic performance was pretty much preserved, but we managed to reduce the noise, as you can see here, especially at lower velocities at mid-range, by quite a few dB. So when it comes to porous materials, traditionally, especially in the 10 years ago, before that, we used to just buy porous materials, metal forms or plastic forms, and the supplier used to just give us the PPI number for it, and then it was on us to characterize the porous material. Now we also have additive manufacturing, and you can design, mathematically define your own porous material. I've put some of the things that we are considering: Schwarz, diamond, and gyroid surfaces. You can do the mathematical definition yourself. You can play with them. You can apply. You can introduce coefficients. You can change the constant, and you can come up with different type of porous medium. And then using proper additive manufacturing, which may sound easy, but it takes quite a bit of time to master it. You can have your own porous material with the right porosity and the properties you want to test. I've put some examples here of the sort of things that we have been doing. You can see the lattice structure, Schwarz P, sine wave based extrusion, and we have applied that to the leading edge of an airfoil. When it comes to porous medium properties and what is important for us as aeroacousticians, these are the things that we do want to know before we start our studies. So we need to know the porosity of the porous material. If you define it yourself, it's easier, but if you have a sample, it's not so easy. Permeability is another important parameter, because we need to know how easily the flow can get into the porous material. Tortuosity can be also important, but not as important as the first two. Roughness is very important, because roughness will create roughness noise, especially at high frequencies. So we do need to have a good understanding of how rough the surface is and try to avoid it if possible. Acoustic properties, we do need to know acoustic absorption is not that important, because the main mechanism of noise reduction here is not by absorbing the sound, but by controlling the flow. But still, when interacting with CFD colleagues, we do need to give them some idea of how much absorption we expect. On the aerodynamic and aeroacoustic side, we do need to measure the flow and understand how the flow interacts with the porous material, and also noise measurements in the near field and far field. So in terms of porosity, the way that we measure, we have tried all sorts of methods, from dipping the porous material inside water and then trying to measure the rise in water. But the best method that we have done so far is using CT scanning. You can see an example of 3D porous reconstruction. So a laser is lit and you get the projection image on a screen, and this laser machine, this X-ray machine, gives you slices of the different sections of the porous material. Then we use a software to put all those things back together. Then you will have a volume of the image volume of the whole porous material, and from that we can pretty much accurately measure the porosity of the metal foam that we have. In the case of mathematically defined one, is a lot easier because you have generated yourself. You take it into CAD, and from CAD you can very accurately measure what porosity you should have. Next parameter, as I mentioned, is permeability. We have various permeability rigs. We have designed and built various permeability rigs at Bristol. This is one of the long ones. Is 4 meters long. At the middle, you can put the porous section. As you can see, we have pressure taps all the way before and after. And in some cases, we also have pressure taps inside the porous section, just because we want to sometimes understand what is the steady, unsteady pressure fluctuations in the section. This is a picture of the thing, and this is one of the porous samples that could be put in. There's a bell mouth to let air get in or out smoothly, and you can either blow air from a compressed air system or connect it to a centrifugal fan and suck air through this section. This shows you some results of pressure drop versus velocity for different porous material. You see the pictures here from 80 ppi. Ppi stands for pore per inch, all the way to 25 ppi, which is pretty coarse. And the gradient of these things gives you the permeability of the porous material. As I mentioned earlier, surface roughness is also very important for us. So we use this Scanatron ProScan 2100, which is basically a laser scanning device to measure the roughness. What it does, it scans the surface fluctuations, and we take a statistical average of that, and that is the RA factor, the roughness factor that we need for defining the roughness of the surface. If you measure all those parameters, you can come up with this rather complex figure. You can see on the on the x-axis is the porosity. For the cases we consider here, they are often over 70%. On the left y-axis, you have the permeability, and on the right one is the roughness factor. So we call it a porosity permeability roughness plot. 80 ppi, 50, 45, 35, and 20 ppi have been tested for this particular measurements. And you can see that it sort of has a quadratic behavior. And the main message here is that the higher the porosity, i.e. Less material, the rougher it gets, which makes sense, and also more permeable, easier for air to flow in. Is this good? Not so much. For aviation purposes, we don't want something with very large pores, because that means higher maintenance and more fragile. We prefer something that has very small pores, but with very high permeability. That's sort of the magical thing, that the holy grail of porous material for aerodynamic, aeroacoustic purposes that we're trying to find. And for that, we have been now 3D printing our own porous materials. You see all sorts of cases that we have done. This is some examples of different families and different sizes. So decreasing pore size on the y-axis, decreasing porosity on the x-axis and y-axis. Just some examples, we have done over 100 of them and then tested them for porosity permeability. And as I mentioned earlier, 3D printing may sound easy, trivial, but it takes quite a long time to find the right 3D printer for it and the right technique to print it. So we have tested quite a few samples over the past couple of years. This is a collaboration with Embraer, the Brazilian aircraft manufacturer. You can see we have done a lot more cases than the previous plot. The porosity here is changing from 30% to 90%, and the permeability, you can see that the range is also quite large. The interesting thing that we did not see in this measurement, but now we see in this measurement, is that you can clearly see two areas at low porosities between 30% and 60%. It seems it doesn't matter much what the what is the porosity, how much is the porosity. You have a linear, you have a constant sort of permeability that you can get, and then after that, for higher porosity, you have a linear behavior between porosity and permeability, and that's the line. Obviously, 90% is already very high. So from our point of view, the best permeability will be something in this range, because this will be too porous, and then lower than that, it doesn't matter much. So in that sense, if that permeability is suitable for you, we can use some of these materials that have very low porosity, and for aviation sector is preferable. So moving on to different applications, I've picked 4 applications that we have been trying over the past 4 or 5 years with different industrial partners to show you how we have used the porous material and what results we have obtained. I will begin with this blunt trailing edge and then move to boundary layer interaction and then bluff bodies, and then if we had time, I will also present something about the leading edge interaction, which means turbulence interaction with leading edge and reducing noise by introducing porous material to the leading edge. Let's see how much time we have. The good thing is that there are different problems, so if we run out of time, I can just ignore the last one. So let's begin with the blunt trailing edge. As I mentioned earlier, this is a representative of flat back airfoils. If you look at the wind turbine blades, the outboard part is pretty sharp, the trailing is sharp, but inboard part, for mechanical purposes, they do not make it sharp. They have a blunt trailing edge. This can cause vortex shedding and associated noise. We didn't want to, as an academic, we didn't want to use an airfoil, so we came up with this flat plate case with elliptic leading edge and blunt trailing edge. The niche thing about our experiment is that, so this colored section is the porous section, so you can replace that with different porous material. The niche thing about our experiment is that we instrumented the porous material with microphones. So you have tiny microphones. These are 2mm miniature pressure transducers that we embedded inside porous material to measure the pressure field at the surface of the porous material and try to understand how that will change when you change it from solid to different porous material. 2 main cases being considered, 80 ppi and 25 ppi here. You may argue that putting a microphone inside the porous material is intrusive and may change the flow field inside the porous material, and I agree, but it wasn't done before, and as of now, that's the only method to better understand the surface pressure fluctuations, the unsteady loading on the section. I won't be able to cover everything. If you're interested, this JFM was published 3 years ago and is a very comprehensive one. It's very long and has all the information, but I present some of the information today just to give you an idea of how things change. So we began with flow measurements. This is done using PIV. We have measured the flow field right after the trailing edge. You see 3 cases here, solid, 80 ppi and 25 ppi. You can see that in the case of solid case, the first column is U, a streamwise velocity, and the second column is V vertical velocity. So you can see in the case of the solid that you have flow recirculation right after the blunt trailing edge. So it's fully attached to the blunt trailing edge. So the fluctuation that recirculation causes is transferred directly to the blunt trailing edge, and that is the worst case scenario in terms of noise reduction, noise from the trailing edge. So this blade, this trailing edge, undergoes a lot of unsteady loading because of that attached vortex shedding to it. In the case of 80 ppi, you see that that is sort of detached just slightly. It's gone a bit downstream, but when you go to 25 ppi, it's fully detached from the trailing edge. That recirculation now is happening about 1 H. H is the height of the blunt trailing edge, 1 H downstream. So this thing, this recirculation or the outset of the vortex shedding is not communicating as much with the trailing edge as it used to do with the solid and 80 ppi. And you see later what does that do to the noise. So we have also done the PIV measurements over the section or hot wire measurements for flow velocity. You see we have taken 4 lines, we call it BL1, boundary layer 1, 2, and 3, and 4, and you see the comparisons here between the 3 cases, solid, porous 80, and porous 25. BL1 is just upstream of the porous section. You see the 3 lines pretty much collapse on top of each other. As you go further towards the trailing edge, you see from the solid case, the black line, that you should expect some sort of overshoot in your velocity profile. That overshoot is because you have that mathematical discontinuity at trailing edge, and the flow is trying to accelerate as it goes over the trailing edge and then dives down, and that is what generates the vortex shedding downstream. In the case of 20 ppi, you see that that overshoot is been properly suppressed, it's been killed by the use of porous material. The top row was the mean velocity. The bottom row is the turbulence intensity, or the RMS value of the velocity fluctuation. Again, just before the porous section BL1, the 3 lines collapse on top of each other. But as you go closer to the trailing edge, the BL4, you see that the solid one has the highest level of intensity of fluctuations, followed by the 80 ppi and then 25 ppi. So 25 ppi has managed to somehow suppress that fluctuations inside the boundary layer to a large extent, which I will show you later. That will translate to reduction in far field noise. There's one thing to also observe here, is that increase of turbulence intensity from 20 ppi compared to solid very close to the surface. This is associated with roughness. 25 ppi is rough, and therefore, because of frictional forces acting on the flow, we will have increased turbulence intensity here. This plot, the RMS plot, only gives you a number. It only gives you a statistical value. It doesn't give you the energy frequency content of the eddies inside the boundary layer. And that's what we have done next. So in order to understand the frequency energy content of the flow structure, and to better understand that reduction in URMS or increase, where is it coming from? Is it low frequency? Is it high frequency? Is it because of suppressing the vortex shedding or not? We need to do the PSD. We need to do the power spectral density of the velocity fluctuations. This is what we have done. We have taken hot wire measurements, which is a measurement technique for measuring velocity at very high sampling rate. We have taken measurements again at BL1, BL2, 3, and 4. I've presented here only BL3. I've only presented here BL1, BL2, 3, and 4 at different heights. So the top row here shows this line, which is very close to the outer layer of the boundary. This is the edge of the boundary layer. Then over this line, which is mid-boundary layer, and then very close to the surface. So let's look at the top one. The solid one, as usual, is the solid case. So no porous treatments. You can see a very strong tone here. That tone is your vortex shedding. Because you have a blunt trailing edge, flow accelerates, will cause shedding downstream. You are looking at these three points, the comparison. So this one is this point here. You can see that the red line for porous 80 has managed to bring down the energy content to some degree, but still you see the sign of vortex shedding. Whereas the porous 25, which is very permeable, has fully suppressed the vortex shedding and also reduced the energy content by a good 5 dB over the full frequency range. Then looking at this point, the BL3, again, you see the same thing. The 80 has managed to reduce the energy, but not as successfully as 25. And then later downstream, again, you see that 25 is the best one between the two porous, but you also see this hump. Just remember this hump, I will come to that later. Let's ignore this one, pretty much the same message as the top row. The bottom row is interesting in the sense that there is not much vortex shedding signal observed here. The most interesting thing is this two plot down here. You see that the energy content of 25 is higher than the other two. So unlike the top, the outer layer of the boundary layer, that the porous 25 was successfully reducing the energy content, here we have increased the energy content of the flow because of the interaction of flow with porous material. There is no sign of vortex shedding as such, but the broadband content has increased. And if you remember from this plot, you saw that energy increase here as well. So this is happening over the full frequency range. And this is because of frictional forces acting on the flow because of the porous surface. And that again takes me back to the importance of that RA, the roughness. So we do need to think about roughness effect and noise associated with roughness. As I mentioned, remember this hump, I will come back to that later. Later, we did wake measurement as well. We use hot wire measurement to do the wake measurement and to see what the flow is behaving like after the blunt trailing edge. The legend is the same. So solid is the black line and then followed by porous 80 and 25. You see that the blue one, the case of porous 25, increases the deficit in velocity in the wake region more than the other two. Again, the top row is axial velocity and the other one is the vertical velocity. So the results are pretty much consistent. The deficit has increased. The Reynolds stress profile, so this is again the energy content of the velocity in the wake. So W1, W2, these are different locations. The results are quite impressive. The solid case, you see the energy content to be 3% of the full momentum of the flow. By using porous 25, that has gone down to literally zero, right downstream of the blunt trailing edge. Further downstream, the flow starts developing again and reconstructing the eddies. So the turbulence level gradually increases, but still compared to the baseline, to the solid case, you see the energy content is probably half or even less than the energy content that we used to have with solid case. The top row is UU, axial Reynolds number, Reynolds stress. This one is VV, vertical, and this one is the shear term, UV term. And again, the story is pretty much consistent across. Again, this one is just a number, doesn't tell you about the energy frequency content. We have done the PSD of the flow, again, to understand what the porous does to the energy content, energy frequency content of the structures in the wake. The top row here shows the results along this line. So if you like the lip line, P1, P1. So this is the first point, and then second point, third point, and the fourth point along that line. So let's begin the other way. Let's begin from this very last point. You can see that Porous 25 is reducing the tone and also the broadband. So does 80, but still 25 is behaving better. Coming closer to the trailing edge itself, to this point, you see that again the energy content at low frequency has gone down, but you see that sign of hump that I mentioned before. If you don't remember, it was here. So that hump is again showing itself. So this one was measured up here, and this one is measured very close to the trailing edge. The bottom row shows the power spectral density of velocity along the center line. You see in the case of Porous 25 is suppressed to the extent that our measurement is no longer valid, is very, very low. But as I mentioned, further downstream, the flow start developing again, and the energy will come up, but still is lower than what it used to be. But what is interesting to us, so we knew that the energy content is going down, so it is interesting and industrially important, but the more interesting academically was what is broadband hump doing there, where that comes from. Is it because of roughness? Is it because of something going on inside the porous material? We don't know. That led to more investigations. This I will show you some results about those investigations in a few slides later. This slide shows you the span-wise coherence of the signals. What does that mean is that we have done coherence between microphones distributed along the span. So if you see those P7, P8, P9, 10, and 11, these are microphones placed along the span. And what does that do? So if you do a coherence between P7 and P8, the coherence between those signals will tell you how similar the signals are. So if you have a large eddy, large structure covering P7 and P8, you should expect a coherence of 1. Often with turbulent flow is never 1, is something less than 1, because the flow is 3-dimensional. It only can cover certain regions, so that the coherence drops with distance. When you have vortex shedding, which is the case with blunt trailing edges, vortex shedding is a very 2-dimensional structure. So it covers the span, a large part of the span. So we expect high coherence between microphones when you have vortex shedding, and that's what you see here. This graph shows the span-wise coherence between different microphones. So let's say P7, P8, then P7, P9, P7, P10, P7, P11. And for P7, P8, you see high coherence, but there are two certain frequencies that you have very high coherence. These are the vortex shedding frequencies. For 80 ppi, you see that you still have the vortex shedding, but the broadband content has been suppressed. You see the frequency is Strohal 0.2, which is the vortex shedding frequency, but other than that, the energy content has been suppressed. In the case of 25 ppi, is even more interesting. There is no sign of that vortex shedding downstream of the blunt, but there is that hump again, which corresponds again to the hump we saw here in terms of frequency. So there seems to be something going on inside the porous material, because this is the measurement taken right at the surface of the porous material. This is the contour plot of the same thing, so no new information here. You can also use the coherence between two signals to construct the span-wise length scale. So you know how coherent these two signals are at different distances. You can put that coherence into this integral and get an estimate of the length scale of that turbulent structure, i.e. how big the structure is in the span-wise direction. So again, you can see here that in the case of solid case, you have very large structures. And in the case of Porous 25, that is gone down to very small structures, which sort of means the turbulent structures, that vortex shedding, which used to be quite large, is now broken down into much smaller structures, which is also good for noise because larger structures means very coherent radiation from the trailing edge. This is a bit more difficult to understand. This plot shows the pressure velocity coherence. So again, coherence, the same explanation, tells you how similar the signals are. In this case, we have taken one pressure measurement at the surface, this point at the trailing edge, and then we have taken velocity measurement inside the boundary layer at different heights, delta y, to the surface, and we try to understand which structure in the boundary layer is responsible for the surface pressure fluctuations and how the porous material is suppressing that contribution. The top row is solid, and then you have 80 and then 25 ppi. The top row shows that the main contribution is coming from the Estrahol 0.2, which is the vortex shedding, the frequency, both for U and V components. So that is the main contributor to the pressure fluctuations at this point at the trailing edge. In the case of 80 ppi, it's still the same thing, but a bit narrower, a bit sharper. So some of the energy, broadband energy, has been absorbed. But in terms of in the case of PPI, is very different. The vortex shedding is pretty much not there anymore, but you have that broadband thing again appearing, and that broadband hump is very close to the surface as well. So it can't be something too much outside the porous material. It's something either at the surface or inside the porous material. We did a silly task. Because it's porous material, you can't measure things inside. So we had limited things to try. So we came up with this rather crazy idea, and we said let's throw sand inside the porous material and try to cover it as much possible to see whether this is a roughness effect or it is something that is happening inside porous material. So you can see here what we have done. We tried to cover, we put a tape underneath so the sand doesn't go all the way through, and then we poured sand. It was a very difficult thing to do, especially in wind tunnel, because the sand will be just blown away. So we had to add a bit of water, make it wet so it sticks in for long enough for the measurement to be done. So we poured sand at 50%, then 75%, then 90%. So if you fully cover it, then you end up with a solid case, except you have a bit of roughness. If it's 0%, then you're back to your 25 ppi. So if you the black line is full sand, so in other words, solid with a bit of roughness. So when you pour sand all the way, you have the tone, which makes sense because it's a solid trailing edge. So the vortex shedding appears. 90% is very similar to the full sand. After that, 75%, 50%, and no sand, this is what happens. So no sand, you get that hump. So when there's absolutely no sand, that hump appears. But when you have 50% or 75%, that hump goes down slightly. And we managed to kill the vortex shedding. So what this told us was that is most probably something happening inside the porous material, and we called it quasi-cyclic vortex shedding inside the porous material. Is a hydrodynamic field that is happening inside the porous material that is responsible for the pressure reduction and suppression of vortex shedding downstream. If you put too much sand, you suppress that hydrodynamic field inside, and as a result, you will have vortex shedding again. So this was really the hypothesis that we developed as part of that JFM paper, and was perceived well in the community. After all that hydrodynamic and near field measurements, we tried far field noise measurements in the anechoic chamber as well. So we put it inside the anechoic chamber. We measured far field noise at about 1.7 meters away. And you can see how well the porous material works. Again, the black line is the solid case. You have 80 and 25 ppi at different angles, 45, 60, 90, and 120 above the porous, above the trailing edge. You see a dominant bluntness noise, vortex shedding tone in the case of solid case. For the 80 ppi, again consistent with what we had seen from the near field data, the tone is reduced by about 5 dB or a bit more, but also the broadband noise to a great extent. The 25 ppi just kills the whole thing. There is the broadband noise and the tones have gone down. One other interesting thing to be careful about is that 80 ppi, because the pore size is smaller, roughness is lower, it doesn't create that much of high frequency noise compared to the solid case. Whereas in the case of 25, the pore is larger and therefore we have a rougher surface here to deal with. We have high frequency noise increase. So that's the price to pay. If we want to reduce and suppress the vortex shedding, we have to go for a very permeable surface, a permeable porous material, which reduce the noise at low frequency to a very good degree. But then we may also have some roughness noise to deal with. The results of the far field noise stuff is presented in this JSV paper, if anyone was interested. This shows the delta between the porous cases and the solid cases. So it's a contour plot of different velocities, frequency, and 80 ppi take away the solid case, 25 minus the solid case. And what you see here that we have managed for the 80 ppi at these frequencies, which is the vortex shedding frequencies, we have managed to suppress the noise by a good 30 dB, which is quite a large number when it comes to reducing noise. We often deal with 5 dB and we will be very happy if we achieve that, but 30 dB is a massive level of reduction. You can see the directivity here as well. So because we had so many microphones up there, that enables us to do directivity of the radiated sound as well. This is the overall sound pressure level, so it's integrated over the whole frequency range. And you see that level of noise reduction is quite large. This is the solid case, no porous treatments. 80 ppi reduces the noise by a good 10 dB at different angles. 25 is even more than that. And we have done measurements at 20, 30, 40, and 50 meters per second. We have also done near field to far field coherence. So we have taken the signal from the surface and the signal from the 90 degrees microphone and other angles and done the coherence between them. So what this study helps us to understand is how the surface pressure fluctuation is radiated and become far field noise. You can see in the case of solid case at the vortex shedding frequency, there is a very high coherence between the surface pressure fluctuation and far field noise. So whatever we had observed in the near field goes all the way to the far field. In the case of 80 ppi, the vortex shedding frequency has a slightly changed, but again, like before, the frequency range is reduced. And then at high frequency, you see no coherence. In the case of 25 ppi, the porous has basically sucked the life out of the flow structure. There is zero coherence between near field and far field, which means that the near field source is fully suppressed. We don't have any contributor to the far field noise. So this was the first application. Let's move on to the next application. I have 30 minutes, so I try to wrap it up quickly. The next application is bluff bodies. This can have application in all sort of sectors. In the aviation sector, we are interested in bluff bodies because it's a good way to model landing gear system. Is usually a cylinder or a couple of cylinders in tandem configuration, and we try to academically, we try to better understand the flow field from bluff bodies and then come up with methods to reduce the suppress the flow, the vortex shedding, and the noise. All sort of things have been tried. You might have seen splitters being applied, some sort of wrapping structure being applied. In this case, we have done porous wraps, and I'll show you some limited results here. You have 3 cases here. The top row, let's look at this column first. You have velocity measured using PIV. The top row is the solid case. Then we have a 45 ppi wrap around the solid cylinder and a 20 ppi wrap. The first column is velocity. The second column is the energy content, or turbulent kinetic energy. You can see from velocity again, like what we saw previously from the other PIV measurement for blunt, that we have a recirculation area here downstream of the cylinder. When you apply the porous, because the boundary condition has changed, the slip condition has changed, the core of this shedding has moved further downstream, so it's now detached, more detached from the cylinder. This structure is responsible for the vertical and horizontal fluctuations of this cylinder. So the further downstream it happens, the less influence it will have on the lift and drag fluctuations of the cylinder. You see the 45 ppi has pushed it further downstream, and 20 ppi has even sent it further downstream compared to 40 and solid. The more interesting thing from this result is to get the kinetic energy, the energy content of the structure. You see the same pattern here. The high intensity area has moved downstream of the cylinder. The first slide was spherical cylinders. This is square cylinders. In the case of square cylinders, the vortex shedding or the recirculation happens closer to the base of the cylinder, and when you apply the 40 ppi, that shifts it to further downstream, and 25 way downstream, many times the size of the cylinder, which means this structure is very unlikely to communicate with the body itself. The turbulent kinetic energy can be seen here. In the case of solid, very close to the structure, 45 ppi has shifted downstream, and 20 ppi is pretty much not there anymore. Let's move to the third application, boundary layer and porous surface interaction problem. After we did the bluntness case, our collaborators, our industrial collaborators, wanted us to do some more investigation on the effect of boundary layer interaction with the porous surface. So when you have a standard boundary layer over a flat plate and you replace part of that flat plate with a porous section, what happens? And that's what we have done here. We have replaced part of a very long flat plate. This is 1.5 meters flat plate to generate a very good boundary layer of about 1 centimeter, 2 centimeters. And we replaced the mid part with a porous section. You can see the picture here. On the bottom side, we put MDF sheet, a plywood sheet. So we will have a one-dimensional flow condition. So only have boundary layer on the top side, not the bottom side. And as before, we instrumented the porous material and the flat plate. You see these little dots here are the little microphones, miniature microphones distributed over the porous and then downstream of the section. As before, the leading edge is elliptic and we trip the flow so we can have a good boundary layer at the section. The result of this work is published in this Physics of Fluids paper if someone is interested. So we use the same porous metal forms as before. And as I mentioned, we have taken pressure measurements at different points, P1 to P41. We have so many microphones, and we have taken boundary layer measurements at different stations before the porous section, over the porous sections, and downstream. I've already explained this one, so I'm not going to go through the same thing, just to give you an idea that there are different porosities and different permeabilities tested. Before we started tests, we validated the flat plate itself. We demonstrated that we get a standard boundary layer, a canonical turbulent boundary layer. The surface pressure fluctuations was validated with other people's measurements, and also we showed that the surface, the static pressure over the flat plate is pretty much stable, is constant, it doesn't change, i.e. we have a good standard zero pressure gradient boundary layer. Then we started taking measurements. You need to take a bit of time to understand this figure. There are too much going on in here. The top row is velocity and the bottom row is URMS, the turbulent kinetic energy. You see that I put this schematic right on top of the thing. So every measurement on the left-hand side is over the porous section, and on the right-hand side is over the solid section. So you can see that by introducing porous section, we have increased the velocity deficit over the porous section, and that keeps continuing all the way to the solid case. We didn't see much difference between the velocity profiles between the two porous cases, as you can see from the results here. However, for the URMS, that changes slightly. The energy content has increased relative to the solid case, and for the rougher cases, for 25 and 7 and 40 ppi case, the energy content at the near the wall is a lot more than the 80 ppi and solid case. Sorry, just to check, Francois Xavier, do I still have time or?
Yes, you do have time. Maybe we could leave. We can consider having 10 minutes for questions for Q&A.
That should be fine. Yeah.
Okay, good.
Thank you. So again, because this only gives us a value, not the energy content, we have done the PSD of the velocity measurements, and you see here again over the porous section and over the solid sections. This one, the top row, is measurements near the boundary layer surface, boundary layer line, and the bottom row is very close to the wall itself. You can see that the porous section didn't change much. The energy content of the turbulent structures in the outside region or mid boundary layer, this one, but in the case of structures near the surface, the porous 25 and 40 is increasing the energy content quite a bit near the surface, and this is because of the surface friction that the porous section is applying to the flow structures, and you saw the signature of that here as well in the mean values. This one shows the wall pressure power spectral. As I mentioned, we have lots of microphones on the porous section and downstream. The first contour plot, the first plot here is P3, which is right in the middle of porous section, and then we have P11, which is just before the porous solid case, then right after the porous sections and further downstream. And what you see here in the middle of the porous section is another hump appearing, and we did the investigation for this one as well, and we linked it to the aerodynamic field that is generated inside the porous material, which is no-brainer when you think about it, because the boundary layer will start to sink in, and there will be a aerodynamic field inside the porous material. But experimentally, no one had ever demonstrated that, and numerically, people never presented the energy spectrum to characterize the energy content of the porous material, of the flow field inside the porous material. This plot shows the contour plot of the same thing. So that line is the line between the porous and solid, and you see a rise in energy content of the pressure at low frequencies right before the junction. We did our silly sand test again, and I'm not going to bore you. We demonstrate the same thing, that the hydrodynamic field inside the porous material is important. And that's something that requires more research, especially on the numerical side, because there's so much we can do experimentally. Our measurement is intrusive and not ideal. I'm going to pass this one and this one. The results are there, so if you're interested, please refer to the paper. This plot shows the autocorrelation of the different microphones P1, P3, P11, all the way to P41, which is the last one. So the solid one, as before, is a solid case, and the other ones are different porous material. The autocorrelation is a measure of how signal is correlated with itself. So if you move it in time, how long does it take that it will lose its correlation? For the standard turbulent boundary layer solid case, this is what we expect. But when you have porous 80, 45, 25, you see that you go negative with your correlation. This is typical of recirculation phenomena. So when you have recirculation, the signal will have a negative correlation with itself. So again, this is an indication that something circulating inside the porous material is happening. Velocity pressure signals, again, we have done the hot wire and surface pressure and done coherence between the two signals, and the observations were very similar to what I just presented for the blunt case, again demonstrating the existence of a high dynamic field inside the porous material. I'm not going to go through every single plot here, otherwise it will be a bit boring. We also did a study on the length of the porous section, how long the porous section needs to be for that high dynamic field to exist. If you have it very short, so you see the PLX 60% of boundary layer thickness, that high dynamic field goes down. So you have a much more compact high dynamic field inside compared to the solid case. As you increase the length of this porous section, you gradually have more space for the boundary layer to sink in and to generate something a bit more substantial. You can see the energy content going high and the frequency going low, which means the structure is now getting bigger and bigger. Again, there is a lot going on in the plot. Please feel free to refer to the paper or get in touch if you want to discuss it further. I better ignore this one. Is a lot going on again here, but the main message is the autocorrelation signal again. So the circle one is a solid case, so no recirculation, as the autocorrelation goes from 1 at time 0 to 0 at large time lag. But in the case of porous cases, you have this negative value, which is indicative of having some sort of recirculation inside the porous material. So the flow is recirculating inside the porous material. The last application I wanted to present to you, and is industrially quite relevant, is leading edge noise problem. So this problem is relevant to the cases when the incoming flow is no longer laminar, is turbulent. When you have turbulent flow interacting with an airflow, you will have what we call it leading edge noise. So the noise is no longer coming from trailing edge noise, but is coming from the leading edge part of the airflow. Why this is relevant? Because it happens in all sorts of places. If you look at, for example, a jet engine, you have the fan and then you have the OGV system. The fan is going to cause quite a swirling flow going inside the duct, and that will interact with what we call OGV, which is job is just to straighten the flow. The interaction between the flow field from that one with the OGV can be a source of noise. You have contra-rotating propellers. The wake from the front one will interact with the rear one. That will be another source of noise. So we have lots of applications, and we would like to see how we can use porous leading edges to reduce the noise. We built our test rig. In order to generate turbulence, we put a grid inside the nozzle that is responsible for generating turbulence. Without the grid, the wind tunnel has a very, very low turbulence intensity. With the grid, we can change the turbulence intensity to between 5 to 10%, which is a high value, and that is ideal for turbulence interaction noise. We put the airflow inside, and you have the far field microphones to measure the noise, and you can see that The porous section is interchangeable. You can take it out and replace it with different porous sections. This shows you the setup. You have the far-field microphones, the anechoic chamber, the nozzle, the test section, the airfall, and the airfall, as you can see, is fitted with lots of static pressure and dynamic pressure sensors, so we can observe what is happening over the airflow as well. We have tried all sort of porous material, 25, 45 and higher, and also 3D printed our own porous material. This is very much an ongoing project with industry, so still in the process. The first round of data is collected and we are post-processing, but I have some very preliminary results to show you. You can see different cases that we have considered here: porous leading edge, porous slightly after the leading edge, different porosities. But the general message is that we can reduce the noise at low frequencies, but it comes at the cost of high frequency noise increase. This is still good enough for us because in aviation, low frequency is the annoying one. The high frequency, given the distance, let's say from your aircraft to people living on the ground, you have a mile or two. But the high frequency is going to be attenuated in atmosphere, but the low frequency will travel long distances. So this is not a bad news as such, although we try to improve and reduce that noise as well by having smoother surfaces, but in general is a good news. Directivity also tells us the same thing. You see the directivity plot between three cases, solid 25, 50 ppi at different frequencies. In general, you see noise reduction. At high frequencies, it becomes comparable, or higher levels is seen from porous cases. The same thing from 3D printed cases. Again, noise reduction at low frequency, noise increase at high frequencies. We have done, this is pretty much the end of it. We have seen the observations, and now we're trying to understand what is the source of noise reduction. Is it because of, if you remember, airflow response or the flow condition? We are doing velocity measurements along this line before the interaction. We are measuring the PSD of the energy content of the velocity before the interaction, and try to understand just before the structure interacts, is the porous doing something to the flow structure that reduces the energy content of the flow structure and therefore reduces the noise, or is it simply just a mathematical boundary condition that has changed from solid to porous? The results are interesting. So you can see here, this is the PSD of velocity just before interaction. You can see the solid one is the dashed line, and everything else is a good 5-6 dB below that. The same thing can be seen here at another point a bit further upstream. Oh, there's a typo here, but this is the final slides of this application. This is now linked to distortion theory. So distortion theory says that when the structure is going to interact with the fluid structure, when it's going to interact with a solid structure like the airflow leading edge, is going to undergo some deformation. And this slide shows that we have used different grids. You can see that just before interaction, x is distance from the leading edge. The flow, the velocity undergoes massive change. And also the case for velocity fluctuations, it goes massive change, but surprisingly, rather than going further down because of stagnation, suddenly shoots up. And this is in sub-millimeter before the interaction. So we're talking about very, very close up distance to the leading edge. We're talking about less than a millimeter that this happens, which makes it very difficult to measure. But it seems that the link is there, is about what happens in this distance and what happens to the flow structure that gives us that noise reduction. So in summary, I've tried to present as much as I could for 4 different applications and show you that porous material has, there's lots of interest in use of porous materials for different applications, from boundary layer control to blunt trailing edges to bluff bodies to leading edges. And I have not covered heat exchangers and thermal management, those sort of things. There's a lot of interest there as well. But there's lots of interesting problems, and experimentally it's very difficult to measure, and that's we're trying to develop expertise in to better understand what is going on, not only outside or at the surface, but also inside the porous material, because whatever happens outside is dictated by what is happening inside, and that's the key. And numerically, also important to make that link, which doesn't exist that much in the literature. So, in conclusion, porous material can stabilize the flow, reduce turbulent kinetic energy, and delay vortex shedding. It can also control boundary layer, but it involves a very complex flow physics, which requires more fundamental study. There is a hype in research at the moment in this area, so you may see more happening. And in terms of practical applications, we do need to address a few issues like the roughness. This might be by covering the surface with perforated sheets or some wire mesh or something. This is also something that we are working on with DLR and other industries. In terms of future activities, we are the use of porous material for other aeroacoustic applications like cavity is also underway. Better understanding of hydrodynamic field inside the porous material. This is where we do need our colleagues from numerical and analytical side of porous material to help. Experimentally is challenging. And also smart porous materials and also the 3D more additive manufacturing activities I expect to happen. So that takes me to end of my 78 slides.